Hello, my name is Kadiatou Diallo. I'm a sophomore at Lawson State Community College, and this summer I completed research at the University of Texas at Dallas in the Software Testing and Quality Assurance Lab, and the title of my project is An Experimental Comparison of Mutation Testing Tools for Python. I quickly want to go over the table of contents. So we first have an introductory paragraph, and then background. I'll go into depth of what mutation testing is, the steps, the theories, and the processes, and some of the limitations. The third section will be comparative analysis, where I will go over my experimentation process. And then the last section is the conclusion, where I discuss improvements and future directions. Mutation testing is a fault-based testing technique that alters codes by introducing synthetic bugs called mutants. These mutants syntactically change the code to assess whether the test suite can catch and kill the mutants. Mutation testing dates back to the 1970s with significant research from Richard DeMillo at Georgia Tech, and first started mutating source code with the Fortran language. Him and his team developed Mothra, a very old mutation testing tool that laid the groundwork for newer mutation testing tools, and more research arose for languages like Java and C, and now Python. This research aims to evaluate those existing Python mutation testing tools to judge their accuracy and effectiveness in terms of performance and other criteria to show their limitations and advantages. Now we will get into the background. Mutation testing is based on two key hypotheses: the competent programmer hypothesis and the coupling effect hypothesis. The competent programmer hypothesis suggests that the quality of a software system depends on the skill level of the programmer. In other words, a more skilled programmer is likely to write better, less error-prone code. The coupling effect in mutation testing also suggests that by detecting simple faults in a program, you are also likely to detect more complex faults. This means that effective test suites for simpler mutants will generally catch complex faults as well. If you see above me here, you will find a mutation testing flowchart of sorts. Mutation testing requires a program and a suite. Next, you have to identify what mutants can be generated based on the components of a program. After the mutant generation, run the test suite and see what outputs were produced. The next step is to evaluate how many mutants were killed and how many survived. Killed means the test case was successful. Surviving mutants mean they were undetected by the test suite and need to be altered. Finally, a mutation adequacy score needs to be addressed. This is calculated by dividing the number of mutants killed by the number of mutants generated. If the score is 100%, the test cases are robust. Anything less means the test should be altered. Mutation operators are a very important part of mutation testing because these are what introduce faults into a program to evaluate the effectiveness of the test suite. Every mutation testing tool has their own unique mutation operators and names, but some are universal like the ones above. There will be operators whose functionality is to alter arithmetic expressions or logical expressions. The design and application of mutation operators differ across programming languages due to their unique syntax, semantics, and constructs. So think of statically and dynamically typed programming languages like Python versus Java. Their mutation operators will look different when you get to more complex test suites. Mutants can be injected into programs via the source code or abstract syntax trees, also known as ASTs. Source code application means that working directly with the text of the code, like editing a document. This allows for easier mutant injection, but ASTs take it a step further with the precision. This is a tree representation of the source code. Applying mutants to this structure allows for more syntactically valid and meaningful mutants, but the complex nature of trees and traversal methods, as well as the computationally high cost of turning source code into ASTs every single time you run a mutation test, makes it a difficult technique to apply and maintain. The next 3 slides will be about current mutation testing tools for Python. MutPy here is a mutation testing tool that parses Python source code to apply mutants to the AST. MutMut is a mutation testing tool that applies mutants to the source code. Poodle is a mutation testing tool that applies mutations to the source code but attempts to reduce runtime with parallel execution. Parallel execution involves running multiple tasks simultaneously to speed up processing. In the context of mutation testing, it means executing different test cases or mutations at the same time using multiple processors or cores. This approach helps to complete mutation testing more quickly and efficiently by dividing the workload and making better use of available computing power. Some challenges and limitations of mutation testing can include high computational costs. The generation of mutants increase as the program under test increases. Functionally equivalent mutants, which behave identically to a program, they still consume resources and they don't help the test suites improve. And finally, incompetent mutants, which means they don't help the test suites at all and they skew the mutation results because they are either found or not found by the test suite. Now let's move on to the comparative analysis. In this section, I'll be analyzing different components of the mutation testing tools to identify their advantages and limitations. The table below includes tool-centric criteria. The latest version of each tool is listed, with MutMut being updated in May 2024, Poodle in February 2024, and MutPy being last updated in November of 2019. All three tools are compatible with Python 3.11 or 3.11, which is the most recent Python update. Documentation is very important because it tells users how and why the tools work. All three tools have a PyPy page, or PyPI page, which is a repository for Python packages where developers can publish and share their software libraries. Only MutMut and Poodle have a Read the Docs page, which is where extensive information about the tool is located. All three tools have a command line interface or a CLI due to the computationally expensive nature of mutation testing, so this is an optimization technique. Now I will touch on mutation-centric criteria, which will include mutation operators and mutation application techniques. Test modules refer to the available Python test libraries, unit tests, and PyTest. These are imported into your test suite. MutPy and MutMut both support unit tests and PyTest, while Poodle only supports PyTest. Mutant categories are how different mutants are grouped together based on their nature. So arithmetic, logical, statement, etc. MutPy has 11 categories, MutMut has 9, and Poodle has 7. MutPy has 20 mutants available along with 7 experimental mutations. MutMut has 13 and Poodle has 12. MutMut was created in 2012, so it had more time to be developed overall. Mutator application technique is important because it determines where and how precise mutations are applied. MutMut and Poodle apply mutations to the source code, while MutPy applies mutations to the AST. Now I will be discussing the experimental programs I will be assessing the mutation tools with. I developed 2 separate programs and test suites to match because finding suitable open source software technique with readable code, documentation, test suites, and compatibility with the tools was a difficult task. I chose these projects to see how mutation tools operate at a basic level. Calculator is a simple program with 4 functions. I developed this to do an analysis of arithmetic-based mutation operators. It is a basic calculator at a low level. The functions are addition, subtraction, multiplication, and division. Book Library, on the other hand, is a program with 9 functions and 27 lines of code, and this will be an analysis of logical mutations. Here are the mutation results for each of the programs. So for the calculator program, the number of mutants that were produced varied greatly, with MutMut producing the most with 61 mutants, Poodle with 17, and MutPy with 9. Speed also had huge gaps, with MutPy being the fastest with 3.26 seconds runtime, Poodle with 11.237 seconds, and MutMut being the slowest at 27.401 seconds. MutMut killed the most mutants with 58 mutants dying, and 3 mutants survived. Next is Poodle with 13 killed and 14 survived, and MutPy with 4 mutants killed and 7 survived. So the mutation scores were MutMut had the highest at 95% mutation adequacy score, Poodle with 76%, and MutPy with 44%. For the book library program, the number of mutants that were produced varied greatly, with MutMut producing the most at 70, Poodle with 40, and MutPy with 10 mutations. So even though the lines of code varied between each program, MutPy stayed mostly stagnant. Speed also had huge gaps, with MutPy being the fastest once again at 3.9 seconds, Poodle with 18.3 seconds, and MutMut being the slowest once again at 29.049 seconds. MutMut killed the most mutants once again, with 59 mutants died and 11 mutants survived. Next is Poodle with 27 killed and 13 survived, and MutPy with 5 mutants killed and 5 survived. So that was actually a 50-50 chance. Mutation scores, MutMut had the highest once again with 84%, Poodle had a 68% mutation adequacy score, and MutPy had a 50% mutation adequacy score. These are the observations that I had after running the mutation testing trials. Each of the outputs of the tests physically looked different. Poodle's output was very long, actually showing a logo, mutations being killed in real time by line, and exactly what mutants were inserted where in the source code. So computationally more expensive, but it wasn't the longest tool to execute, so it did not take as much time as MutMut. It was in the middle every single time with the time. MutMut took significantly longer than every other test, but produced the most mutants, thereby having the highest mutation score. But it does not show what mutants were produced or how long the process took, so I actually have to time it externally. This raises the concern of unnecessary, incompetent, or even equivalent mutants, and I do not know if that was very necessary for all of those mutants to be produced. MutPy produced so little mutants, I was actually worried. Does that mean that many mutants weren't necessary, but was the suite tested well enough? I'm also not sure of that. In the command line, there was many problems. I had a lot of problems navigating file paths. It caused me to spend hours just trying to get the tools to run. MutMut and MutPy required me to enter full file paths to run the test, while Poodle had me only type its name as a command and the test was executed. MutPy, being the oldest tool with its conception in 2012, worries me to think that there have been no advancements in the interface 12 years later, and the latest update being 5 years ago has me to believe that the tool will not update anymore. Meanwhile, MutMut and Poodle were updated earlier this year. The mutation adequacy score is very important because this will assess whether the test suites are suitable for the program under test. But every mutation score depends on the specific tool being used and the size of the program. For both programs under test, the results varied greatly, with the mutation score ranging from 44% to 96%, spanning over all three tools. So none of the actual tests actually had a 100% mutation adequacy score. So none of the programs had robust tests. We will now go over some of the conclusions. Here are some of the improvements I proposed. So one of them would be to improve the mutation output. Poodle's method of a real-time mutation test, along with showing exactly where mutations were injecting, was a good practice that MutPy and MutMut did not have. This will allow for easier readability of code and the exact test suites that need to be improved, because if not, it'll have somebody going in blind to their test suites, and it's just not very helpful. Another one would be to implement a graphic user interface, or GUI, to allow for better usability of a tool. Even though a CLI might be better computationally, it is dependent on what the tool's goal is, accessibility or research. And last is a test suite recommendation system using AI could be beneficial, and it can save time when altering test cases, because receiving a perfect mutation score the first time you run the mutation tool is very difficult. And the main goal of mutation testing tools are to make sure that your test suites are robust. Why have the mutation testing tool if you don't have recommendations on how to make the test suites better? The point of mutation testing is to get a 100% mutation kill score or adequacy score. I did not receive any of that for the tools, and more training and software testing is needed to create more robust test suites. All the tools were difficult to navigate at first, and being able to find a suitable program under test, or PUT, to use for experimental evaluation tools was something else. You need to make sure that the open source software you find has suitable test cases, readable code, and can compile. The tools are handy but computationally expensive, and the bigger the test, the slower the tool. There needs to be further experimentation to observe other behaviors that I was not able to catch in the code. Some of the future directions I want to take is to apply mutation testing tools to larger programs with 100 lines of code or more, to develop more complex test suites and assess the tools further with more complex criteria. I also want to experiment with Cosmic Ray and Mutatest, which are other well-developed Python-based mutation tools. Thank you so much for tuning in and watching me present on the experimental evaluation of mutation testing tools for Python. If you have any questions, you should find my email. You probably got my number. Just check me out and I'll answer some of your questions. Thank you so much.